Welcome back. Welcome back to the course Responsible and Safe AI. I hope you're enjoying and participating. We see a large number of people asking questions in terms of the answers that were provided. Some of you actually posting information from other articles that you've read. It feels very nice for seeing students participate well in the mailing list. We hope you continue doing that. So what we are going to do in this part of the course is we are going to look at this idea called interpretability, transparency, probing. All three words kind of go hand in hand. Sometimes they are even interchangeably used. So we'll see what it means. We'll see what these ideas entail. So this is a slide or an idea that we saw a long time back in the course, which I think is in the week 1. What is an alignment problem? This is just a refresher for you to remember that the alignment problem is making sure that what we want the system to do and what the system is doing is the same. Right? If you remember the rogue AI slide, where this board goes around and things like that, or a chat bot that we have seen before, where it kind of says some things against the company. Right? All of that is the alignment is not done well. That's the idea. And we want to do all of these interpretability, transparency, and probing the models, interpret the models and see what the models are doing, making the models transparent. All of these ideas are built on this broader theme of saying make the alignment between the system and the user better. So what will we cover, and what is the reason for studying transparency also, right? So the idea of transparency is to try and provide clarity about a model's inner workings. As I said, you want to know what the model is doing. You want to know why the model is doing what it is doing, right? Why it is doing what it is doing. Model changes can sometimes cause the internal representations to substantially change also, right? Some changes in the models can change, so we would like to understand when the models process data differently. So you want to know when the models change something, you want to know why it is changing, what it is changing. And it also makes the deception and other hazards. So we'll see some examples of these deceptive nature and hazards in a bit. But transparency allows us to know all this when the model does it. So provide clarity, understand, monitor. If those were the keywords that we'll have to take about why we are studying transparency. So there are many methods that people have devised, and lots of details are around this transparency itself. But I'm going to condense and walk you through some popular, some basic ideas of transparency. So one of the ideas is called pixel attribution methods. Particularly, these are for images. Highlight the pixels that were relevant for a certain image classification by neural network. So if you look at this example, so it is actually highlighting some parts of this image here and here. Pixel attribution. It is pixels are attributed here for identifying something in the image there. Right? Pixels are colored by the contribution to the classification. Right? So you want to, later you will see examples that you've given an image of a dog and you want the model to classify it as a dog. You will see some heat map of saying where the model is looking at while making the decision that it's a dog. Right? So that's the idea of pixel attribution. This pixel attribution method itself actually is used or said in many different words. So for example, sensitivity map, saliency map, pixel attribution map, gradient-based attribution methods, feature relevance, feature attribution, and feature contribution. Different ways by which the same idea for pixel attribution is done. But feature attribution, if you see, it is actually done at a slightly, at a different level where you're talking about each of the features, right? What feature is it contributing? So pixel attribution is a special case of a feature attribution, but looking for images. That's what a pixel attribution is. Otherwise, feature attribution, and if you think of text, if you think of other modes of data, then probably feature attribution will be the abstract definition of how you can do transparency. Feature attribution explains individual predictions by attributing each of the input feature according to how much it changed the prediction. That's the idea. So because if you see, this is agnostic to the mode, right, which is text, image, etc., video, etc. Features can be input pixels, tabular data, or words. Any of this could be input data, and the feature attribution could be features of the images, features of the table that is provided, features of the words that is provided. Right, so that's pixel attribution. So we'll continue looking at some methods in pixel attribution itself. Occlusion or a perturbation based. So in this case, it is SHAP and Lime, which we will see it in detail after a bit. But methods like SHAP and Lime manipulate parts of the images to generate explanation. It doesn't bother about the model. It looks at the images, perturbs the images a bit to see how you can understand the way the attribution, the pixel attribution can be done. You will see some examples where when we do the SHAP and Lime, you will understand a bit more of the inner workings of how Lime and SHAP is done. But for now, the idea is there are under pixel attribution methods, there is this idea called perturbation methods, of which an examples are SHAP and Lime. Then there is also gradient-based methods. We are going to spend some time on gradient-based methods now, which is many methods compute the gradient of the prediction or the classification score. Each and every image is decided on whether this is going to be a cat or a dog. Right, whether this is part of an image of a cat or a dog. You're going to classify that with respect to the input features that is provided. The gradient-based methods mostly differ in how the gradient is computed. So we'll see some examples of gradient methods. So here is one, right? Here is some examples of how these gradients could be calculated, how these methods have also evolved, right? StyleGAN 2 and StyleGAN 3, these are some methods that are available for pixel attribution methods. So images are here. We'll walk you through what these images are. It's texture, sticking, figuring out the texture of the images. Left is average of images generated from a small neighborhood around the central latent. So if you look at it, it takes an image, it takes a part of an image, and then does neighborhood around that image, and then decides how the image should look, what the image is. All right. So in this method, it is kind of average. So it is doing the average of the neighborhood pixels that are available. So if you see, it's slightly kind of smudged here, whereas in the other central thing, it takes the central part of the image that is provided and does the average of the images. Let's look at examples of StyleGAN. Let's look at examples of StyleGAN 2 and StyleGAN 3. This must be STYLE, StyleGAN. So in this case, what we are going to look at is we are looking at, in the left, images of generated from a small neighborhood around central latent is a top view. right? So there are two methods by which these images are done. One is the neighborhood, and the top one is at the central latent of the image is used. Pixels are used. In the right, if you see, small vertical segment of pixels are taken. So if you see, here is a small vertical right, segment of the pixels are taken, and then they are stacked horizontally, which is why you see the hair here stacked horizontally. And in StyleGAN2, it is done this way, and in the method of StyleGAN3, you can also see the hair movements also can be captured. So what it is saying is that it is explaining that how these method called StyleGAN2 and StyleGAN3 actually are processing these images, and how it can be actually used for pixel attribution methods. Here are some, again, internals how. So here we just look at how the, visually you can say how it is done, right? So this is doing, this is taking the average of neighborhood of images. This is taking a segment of it and doing it. Now, if you look at how it is done slightly internally, details glued to the image versus surface, right? And internal representations are different. Internal representations, so if you look at StyleGAN2 here, internal representations, if you see, this is how it is, right? In the later latent interpolation, which is how, meaning looking at the input image, the face here. In StyleGAN3, it is actually does not matter whether it is equivariant to translation and rotation. Translation and rotation are two different methods. So you may remember some parts of the lectures before where we actually talked about how images can be transposed, all that. So that's the idea for translation and rotation, help in identifying important properties better. Right, so if you see here, it's actually identifying the eyes, right, and different, so the nose and everything. In the StyleGAN3 takes, it is able to identify them better. And the argument that the StyleGAN3 paper was making is that it was doing better than StyleGAN2 in terms of tasks like texture sticking, tasks like identifying images or what is in the image classification. Let's take, if you were to do the downstream task as image classification. Okay, again, why are we seeing this here? We are seeing this because it is providing you, right? It is actually helping us to understand, look, this part of the image is what is being used to decide that the eye is here. That's what in the context of transparency, that's what is in the context of pixel attribution method. Now let's look at saliency maps. Saliency maps, again, is a way by which we get an insight of how the pixels are used to classify. So the input image is here, and then the predictions is what is the prediction. I want to find out con in this image. So how does it work? It performs a forward pass of the image. Image is taken and a forward pass is done. Compute the gradient of the class score of interest with respect to the input pixel, set all other classes to 0. I'm looking for a con, so I do the, all other classes are kept to 0. And if you see, that's what broadly it is capturing here, right? Broadly it is capturing here. The class could be also a face, the class could be also a human being, the class could be a human being with a con. Visualize the gradients. So here is what the gradients is that is being visualized. You can either show the absolute value or the highest negative or a positive contribution separately. So here what it does is it is just showing you different parts of the image in the gradient, how it is contributing to deciding whether there's a face here, whether there's a con here. In mathematical form, this is what it is of the gradient itself. So you will see this part changing in different next few slides. Don't worry too much about if you don't understand the mathematical equation itself. But the abstraction is that here it is just a gradient. I'll show you one or two more methods how these things change. Look at here. It actually does a small variation in the gradient itself, and it also does some average after that. So in the saliency maps, this method is called a SmoothGrad, and the last one is called just gradient method. Right? In the SmoothGrad, it generates multiple versions of the image of interest by adding a noise to it. Right? You just generate this image, add some noise to it, and create more and more images. And this idea of adding noise, you will see more also as part of this a module where you will see in Lime more noise is added. Perturbation method, right? That's the broader idea for adding noise also. Create pixel attribution methods for all images. So you take one image, create multiple images of it, create the gradient of this, and then average it out. So that's what this is, right? And then we are also adding some noise and with the image that's here, and you do the average for all of them. Right? Average the pixel attribution maps, which is this. So now if you see the gradient and the SmoothGrad seems to be slightly better of identifying, let's take Con here. Right, so let me show you more examples of these methods. So here is an example where the input image is greyhound, here it's a soup ball, here it's eel, but if you see the image, so these are images of a dog classified as a greyhound, and ramen soup classified as a soup ball, and an octopus classified as an eel. So the images are dog, soup ball, and octopus, but it's classified as greyhound, soup ball, and eel. Right? But why it is done is what our interest, right? Transparency, that's what we're looking at. So if you see, it's kind of picked up some pixels here. In SmoothGrad, it's kind of a little bit better. It probably identified the book also here. In this case, it identified probably the food in the ball. In this case, it identified again some pixels here, because of which it actually decided that it is eel. Right. Idea of a gradient, idea of a SmoothGrad, and idea of given an example, how does it work from top to bottom. In this case, we were just doing Con. In this case, there are many different images here. And now let's look at another method, which is called guided backpropagation. Backpropagation we already know. Backpropagation of the intermediate negative evacuations, and gradient zeroed out, that's only positive gradient. So what happens is, in this case, the backpropagation is done, and negative activations and gradients are zeroed out, which are not positive, are removed, and that's the only part that is shown here. So if you remember here, we can actually represent it. You can either show the absolute value or highlight the negative or positive, whereas in this method, it is only showing you positive gradient. Right? So that's what this is. Right? So multiple methods. Next, I'll show you more methods here. We saw only few, but here is a list of all the methods: Lime, SHAP, gradient, SmoothGrad. There's a whole lot of methods by which you can actually identify the pixels that are attributing for classification of the image. And later I will also show you where there are source code for doing all of this yourself. I highly recommend some of you to take a look at it, play around with it. But for now, the idea is, look, there are methods by which you can actually find out, understand which part of the image is being used for classification. There are many methods built, and here is a list of methods that exist, and some of the methods that we have seen in detail. But the problem with these methods are that these can be deceptive also. If you look at this. Explanation using attention maps. This is a test image, but see it is actually classified as evidence for an animal being a Siberian Husky. Why is it deciding as a Siberian Husky? And interestingly, it also decides that it's actually a flute, but it is using all of this to make the decision. So the problem with these salience maps is that to create a fun to look at visualizations that do not actually inform us much about how the models are making the predictions. Right? So we need to understand why it actually decided also to be a flute, right? Or a dog. So here's a nice method by which if you actually change the layers in terms of the neural net, if you change the layers, what should happen, right? So if you randomize the layers, some saliency maps do not change much, which suggests that they do not capture what the models has learned. So if you look at here, so these are gradients, guided propagation, SG we just saw, SmoothGrad, right? And if you see here, so this is the original explanation. And if you see, these are the different layers, right? Cascading randomization from top to bottom layers. What is happening is, if a model captures a higher level class concepts, then the saliency map should change as the model is being randomized, right? So if the layers are making a difference, and if I randomize the layer, something should change. Sole visual inspection can be deceiving. So the point that to get across is that if you just use only visual cues to decide whether it's husky, whether it's a flute, it's going to be a problem. There's going to be errors. That's what this is trying to say. This is trying to say that if the layers change, eventually things should change. If it doesn't change, there's something going on, right? Some saliency maps do not change much, which suggests that they do not capture what models have learned. And these are the methods that we saw, right? Guided backpropagation we saw before. So if you see the layers, cascading randomization from top to bottom layers. So therefore, by changing the layer, the saliency map should change as much is being randomized, as the model is being randomized. And the conclusion from here is do not use the visual methods, use some of the sanity checks to make sure that the model is able to pin down the reason why it is doing the classification properly. Here are more actually optimized masks for saliency, how you can actually build on this idea for pixel attribution. Some saliency maps optimize a mask to locate and blur salient regions. So if you see here, right, this is not blurring, whereas in this method, if you see, so an example of a mask learned right by blurring an image middle. So this is the image that is getting blurred. Here is an input, and here is a blurred mask that it has learned, right, to suppress the softmax probability of its target class, left original image, softmax scores. So these are scores that are given for while doing softmax on these images. The problem with this is that it's super sensitive to hyperparameters and mask initialization. How do you initialize the mask? Where do you start the mask? All of that actually matters in this method. And the softmax scores are also very useful. Let me show you some more examples. So if you see here, so this is, right? So it's actually learning the mask is here, and it is learning that it is espresso, and the score is very high here. And the maypole also here. It is able to identify it much better because it has learned this through the mask. Right. Again, I would highly encourage you to play around with the code. Later, the pointers I'll show you, actually 3 or 4 of them I'll show you, which all has directly GitHub code. You should be able to try it out yourself also. So this one is original image with the bounding box. So it's actually figuring out what we are looking for. This is cliff, So here is a bounding box, street sign, dragon, pickup truck, right? So different methods that you can think of. The mask one that we saw, gradient, guided backpropagation. So we'll see what Grad-CAM is later, but otherwise here are different methods that input images, how these methods identify the parts of the image for classification. Okay. So let's delve into what LIME is. Again, I put a pointer, so if you're interested, please go take a look at this YouTube video, which explains LIME in length, but I've condensed it to convey the idea for how LIME would work. So LIME works on any black box model. Right? A model is given. I want to understand how the model is making a decision. That's transparency. That's what we saw. Pixel attribution, all of this. So LIME is one of the methods. Model internals are hidden. We don't know how ChatGPT is deciding or Llama 3 is deciding what it is doing. So I want to get into it and see. Works with many data types that we saw before, text, tabular, images, video, all that. Uses prior knowledge. Using prior knowledge, we can validate the explanations, right? So it does some things. So for example, this is coffee source or this is street sign. We can use existing knowledge, probably even human annotation to decide whether it is doing correctly. Again, please go back to the idea for RLHF that we saw before. So this is a big theme of LIME, which is that the explanations that it will provide is so much faithful locally, which is in a particular image, right? In a particular data set, data points around it, it will be very, very faithful. Faithful meaning it would do justice to the decision that that pixel is being used, the data point is being used for classification. But it may not be the same case for globally. That's the idea for, that's one of the theme for how LIME works. Let me walk you through some examples. So let's take if we have data points for patients coming into the hospital. We have a lot of features. Features are data that we have collected from the patients. Let's take their weight, height, blood pressure, sugar, time that they spend in doing exercise. All of that is, let's take features. But here we're just using, let's take two features, even something like body mass index, right? Body mass index, BMI, right? Things like this. We can use all of this as features to, so in this graph, only two features are taken for every patient, and a graph is drawn of the points that are there. Every dot is a patient, and there is some curves that are done to decide that these are patients which may have, model is generated, right? Model is created to show that these are people who have possibility of getting a stroke or not getting a stroke. This is stroke and this is no stroke, right? That's the application, right? You have all the patients, we have collected data, we know all the features of all data for all patients are there, all data for all patients are there. We could generate a model which says that what is the probability that if there is somebody X new patient that comes, whether they would get stroke or not. We could use this model to decide. That's exactly the application we are going to do. There is a user, there's a patient who comes in, and with respect to feature 1 and feature 2, the user falls there. The patient falls there with this feature 1 and feature 2. Now we'll have to decide whether is what is the probability, or if the system has to decide whether he's part of a stroke or no stroke, how would we decide? Right? And please remember, it's not that easy answer also, right? Because the model that we have already built, we can use that, but we'll have to explain whether this is, I mean, is this user very close to the model that is built? Let's take if you have to do just distance, right, close to this, or whether he's in the other space and therefore he's stroke. That's the explanation that we are looking for. That's what LIME is going to help us to study, which is local interpretable model agnostic explanations that you can get. What LIME is going to do is that, so this is a complex model, right? The model is very complex because of these, I mean, all the models that you could think of for these kind of data will be very complex, right? It's not going to be that simple that look, there's a linear relationship between two features for getting a stroke or not. That's a complex model. What LIME is going to do is that, look, it's going to say that we know that this is close to the complex model here. So just do a linear model, linear line here, and say that, oh, this is everything this side. We'll actually analyze it now, and we'll actually generate a lot of data points, assuming that the data of the patient that we have, we can actually perturb that data, right? Perturb that data with other pieces of features that we may have. For example, if this is height and weight or height and BMI, you say that, look, we can actually change one, sort of say, centimeter height and increase the centimeter 1 and decrease the BMI 1, right? So if the height is this, you increase the height by 1, and you say, I'll also increase the BMI by 1. So it will probably go here. So there will be a data point here that is generated. We can create a lot of data like this, right? So that's what, so first step, decide a simple model compared to a complex model that is already there. And now work around with this simple model locally to explain to figure out, classify the patient into a stroke or a no stroke. That's exactly what this mathematical formulation is going to help us. Quickly, so this is all family of interpretable models. From that, we are choosing this G model, simple interpretable model, which is a linear model that I said. F is the complex model of all the data points that are there. Proximity, right? So I said about 1 centimeter height and 1 value of BMI. Going up is what the proximity is. And then this is a simple regression. It could be a linear regression or a lasso regression is what they would, the paper also talks about, can be applied just to keep the model very simple, right? So that's what here, right? So the linear model here. Okay. Again, feel free to go look at the longer video if needed, but here you will get the idea for how LIME works with this explanation that we are looking at right now. Right? So what I drew before is what is here. Lots of data points are created. All these orange ones are data points that are created by changing the two features. And the lasso regression is what I said before. And the nice part about this is two actually things. The LIME method is not going to bother if the data point is so far away from the data point that we are interested in. That's one. Second, if you remember the line, it's going to be faithful locally, which is what this is showing you, which is the darker the color is, it's going to give more weightage. Right, so that's what this is happening. Right, so this is if you look at F and G, F is the complex model, G is the simple interpretable model, which is the linear model. That's what this is. Right, it's just looking at the distance and squaring them and adding a weight to it depending on how close it is or how far is it, right? Okay, so that helps to see how you can actually explain and find out whether now he would fall into the stroke or a no stroke classification. Here is a paper. It's actually very well referred, cited, and talked about method. If you're interested, take a look at the paper also. But of course, the video should also be able to help you. But if you read the paper, come back, and if you have any questions, happy to take them. Let's continue with the idea. So I said LIME and SHAP before. Let's see what SHAP is. SHAP idea is that it's built on this idea called Shapley values, and it's a game theoretic approach, right? And so this idea is that when we have, so here if you see all the features are there, I said BMI before, age, blood pressure, whatever, and some base rate is given, and some output values the models are providing. I need an explanation for each and every feature that is happening. That's what SHAP does, right? It will tell you that, look, the effect of BMI on the model, the decision that is being made is actually positive by 0.1, is negative by 0.3. Right. So the idea is that, so if you think about modeling, so let's go back to this one. If you think of models, it's going to use all these features to make the models, right? And let's do an example. I think here also I put the link to the paper and all that. So let's take, for example, if somebody has to look at the details of application for a loan and decide whether the loan should be provided or not, right? It will have details like age, yearly income, probably credit score, some age, yearly income, and let's take tax paid, yearly income tax paid, income tax paid, some things like this, right? It has all of this, and the model should decide whether the application should be given the loan or not. And if you look at the way that some of these features would work, some of these features are also interlinked, right? Interlinked in terms of, for example, I think there's another thing, retirement age, let's take. There is age of the person, and what is the potential retirement age for a person, how much different is the user, the applicant from that. Some of these features can also be interlinked, will have an effect of each other. Same thing with the stroke also, right? For example, age and let's take blood pressure. There is a relationship, so you can't only study them individually, effect of it. And if you think of the word called ablation studies that people say, right? You want to look at effect of feature 1, feature 2, feature 1 plus feature 2, right? So the Shapley values helps to understand the interlinking also. It enables you to study the model, how the interlinkings of effect of the features are also. Again, I'm not going into a lot of details here, but the idea is it allows you to get a sense of what are the effects of the features in making the decision. It's a game theoretic approach to explain the output of any machine learning model, connects optimal credit allocation with location explanations using the Shapley values. So that's what this is. It uses the features, and it uses the linkages between the features also to decide how much it is affecting the final outcome of the model. That's SHAP. Then there is also Grad-CAM. Grad-CAM is again another popular method for understanding transparency of the models. So let me go through some parts of the abstract of the paper to give you a sense of what is in the paper itself. So what they argue is we propose a technique for producing visual explanations for decisions from a large class of CNN-based models, making them more transparent and explainable. That's the goal. And then they argue that what is the necessity for it, which is our approach gradient-weighted class activation map, which is Grad-CAM, uses the gradients of any target concept, which is say a dog in a classification network or a sequence of words in captioning network. Again, input data could be image, text, that's the idea, flowing into the final convolution layer to produce a coarse localization map highlighting the important regions. It's built on the idea that we have already seen. So then they argue about what the previous methods do. This place is what they argue, what they have done. In the context of image classification model, our visualizations lend insights into failure modes of these models, outperform previous methods with some data, help achieve model generalization, more faithful to underlying models. So that's the Grad-CAM idea again. And here also they put the code and a video also explaining how it works. Our video actually has a demo of uploading an image, seeing which part of the image has the influence on the decision, and understanding the way by which the model classifies the image is what the URL is, YouTube video is. Take a look at it. Right, so that's Grad-CAM. So what did we do now? We just saw what LIME is. LIME is local interpretable model agnostic explanations. SHAP is Shapley additive explanations. All of them are explanations again. Grad-CAM is gradient weighted class activation mapping. Okay. So with the pixel attribution methods, gradient based methods, explanations are visual, detecting important regions is easy in this image, faster to compute of course, fine, LIME and SHAP are expensive. The difficulty is that to know whether an explanation is correct, very fragile, adversarial perturbations produce same predictions. I mean these are coming out of some content that is summarized, but currently the idea is that these models, perturbations produce same results. So just think about it, right? Even here, the way that this has been done, different data points has been perturbed. The perturbation, depending on the perturbations, the outcome also can be influenced. Right? So that's what is mentioned here as a con. Adversarial perturbations produce same prediction, which is bad. Right? Yeah, here are some examples of the code and everything that I mentioned before. Right? This is TF Keras. What it does is it gives you feature visualization, which we'll see what it is in a bit. But we also saw class activation maps, Grad-CAM, Grad-CAM++, Saliency maps. It gives you code for support n-dimensional image inputs. That's not only support pictures but also 3D images, supports batch-wise processing, so be able to efficiently process multiple images, support mixed precision models, support models for multiple inputs and multiple outputs. So essentially my interest in showing these, I think I've kept like 3 of them, is to get you to go try it. Right? Go try it. If you find anything difficult or hard or not able to do it, come back, we'll figure it out together. But the idea is for you to explore. The next one is investigate with a double N. Again, the GitHub code. It talks about the functions it has, gradient, SmoothGrad, all that, and it has different methods. All of this we have seen until now, right? So some of this at least we have seen, guided backdrop, all that. Right. And the next one is DeepExplain. This DeepExplain provides a unified framework for state-of-the-art gradient perturbation-based methods, and it gives you salient maps, gradient, and again, different methods are implemented. Shapley value sampling, all of that is provided in the code. Yeah, try it out. If you find it difficult, come back to us. So we saw we saw images until now, but that has nothing to do with only images, right? The interpretation, the transparency that we want to do does not have to be tied only to images. It can also be for a text. Saliency maps can be used for text modes too. And let's look at the text here. This says, the year's best and most unpredictable comedy. We never feel anything for these characters. Handsome but unfulfilling suspense drama, right? If some of you have worked in NLP or understand, you can actually find out the same idea of pixel attribution, which is again an idea of feature attribution. What feature is contributing to whether the sentence is being tagged as positive or negative. That's now interpretability, right? Understanding what the model is doing. That's what is written here. Also, there are many possible saliency scores for a token. You can find different ways for it. In the image, we talked about gradient as one way. One possibility is to use the magnitude of the gradient of the classifier's logits with respect to the token's embedding. While there is no canonical saliency map, these can be used identifying salient words by writing adversarial examples. Yeah, you could use it for identifying adversarial example, which is the idea is that, look, if these are positive, you can use them in examples that you create, right? So in this case, it says the Y is the gold standard and C is the predicted one. If you see here, the gold standard is positive, it is also predicting it as positive, whereas it is here negative, negative. In this case, it's actually opposite. The gold standard is negative, but it's predicting it as positive. If you remember earlier, I mentioned about this feature visualization in one of the code GitHub link I showed. But here the idea is that to understand what a model's internal component detects, synthesize an image through gradient descent that maximizes the component. Essentially, again, the idea of using the model's internal what it is detecting. So neuron visualization is at a neuron level. What it does is component is a neuron, optimizes the image to maximally activate the neuron. Repeated round of gradient descent, optimize the noise image. So that's what a neuron is doing. When they are put all neurons together, it becomes channel visualization. Like neuron visualization, both gradient descents, loss of channel visualization might be a sum of the squares of all neurons in the channel, lot of squares, right? So if you see, this is multiple neurons. The difference between this and this is one neuron, this is many neurons. And the way that you can find the class channel visualization is you can do a sum of squares of all neurons in the channel. Right, so that's the idea. And here is an example. What it says is maximally activating natural images, which is they are identifying windows. And by this neuron visualization and channel visualization, you can actually figure out exactly where the windows in the images are, and maximally activated. These are examples of maximally activated natural images, how windows were identified. And now when you think about this feature visualization, right, now what we are doing, we are using the features and using at a neuron level and a channel level to understand. there are methods by which you can actually do this and try it out. So I've actually played around with this. Please take a look at it. See, so these are the different models that are available in this link, and you can actually see what each and every layer is doing, and the output of each and every layer, and even at a neuron and a channel level, what it is doing. How it is deciding that a given image is a window. That's what we want, right? That's what in the transparency and interpretability we want to understand. That's exactly what this does. It gives you an explanation for using the method of feature visualization. It gives you a sense of how it is deciding windows, which is in this here. You can play around with different models, different settings, all that. Right. So this one is exactly the image for the windows that I showed you earlier, which is using ResNet v25 and different layers. Yeah. So different models is presented here. Take a look. So this one is specifically for the models of ResNet and what I showed you example. But if you're interested, please take a look at till here, the URL in the next slide. Take a look at it. It actually provides you a lot of interesting understanding of how these models work. Yeah, just 13 important vision models. Okay.